So, when you think about testing Einstein's theory of gravity, you're probably thinking about our solar system, right? Maybe a tiny wobble in Mercury's orbit or seeing starlight bend around the sun. But honestly, that's like testing a race car in a parking lot. To really see what gravity can do, we have to go bigger, way bigger. We have to use the entire universe as our laboratory.
So in this explainer, that's exactly what we're going to do. We're taking a trip to see Einstein's ideas pushed to the absolute limit. First, we'll see how entire galaxies can bend light. Then, we'll check out the light show happening right at the edge of a black hole. And to finish, we'll listen in on the most perfect clocks in the entire cosmos. So, how do you test a theory that's supposed to govern the whole universe? Well, it's actually pretty simple. You use the universe itself. You find the biggest, most massive, most energetic things out there, the places where the laws of physics get pushed right to their breaking point.
Let's just kick things off with a question that sounds, well, it sounds completely made up. Can an entire galaxy, with billions of stars, gas, dust, the works, can it actually act like a giant magnifying glass in space?
The answer is a mind-blowing yes. I mean, just look at this. This is a real photo from the Hubble Space Telescope. The bright blobs there in the center, that's a massive cluster of galaxies. But check out those weird, stretched-out blue arcs around it. That's the truly wild part. That isn't something in the cluster. Nope. That's the light from a single galaxy way, way behind it that's being warped and smeared across the sky by the cluster's incredible gravity. This amazing effect has a name: gravitational lensing. And it's one of the most powerful predictions to come out of general relativity. So let's break down how this actually works. The idea behind it is surprisingly beautiful. Einstein figured out that mass doesn't create a force that pulls things. Instead, mass literally bends and warps the fabric of space-time itself. Think of it like putting a bowling ball on a trampoline. And light, just like everything else, has to follow those curves. So when light from some distant galaxy passes by another massive object on its way to us, its path gets bent. And from our point of view, it looks like that light is coming from several different places at once. And the result is that you can look up in the sky and see the same exact object in 2, 3, or even more places at the same time. And hey, if the alignment is absolutely perfect, the light can get smeared into a complete circle called an Einstein ring. It's a cosmic mirage, literally painted by gravity. Now we can take this idea even further. What if the object doing the lensing is too small or too dark to see? Like a rogue planet wandering through space, or an isolated black hole. Well, that's where a really clever technique called microlensing comes in. Instead of creating multiple images, it causes a temporary telltale flash of brightness. It really is like a cosmic detective story. For a while, astronomers used this to hunt for these invisible culprits called machos. That stands for massive compact halo objects, because they were a top suspect for what dark matter might be. The method is just to stare at millions of stars and wait. When a dark object drifts in front of one, its gravity acts like a tiny lens, focusing the starlight and making the star briefly brighten up and then dim back down in a really predictable way. Now, these searches did find some of these objects, but not nearly enough to explain away all the missing dark matter, so the mystery just got deeper.
And this right here, this is what the evidence looks like. This is real data. You can see the star's brightness is just steady, 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 and then whoosh, it smoothly ramps up to more than 8 times its normal brightness and then fades right back down. That perfectly symmetrical curve, that is the gravitational fingerprint of an object we can't see. And the takeaway is just incredible. We're using gravity to weigh things that are completely invisible.
All right, so from invisible objects to the ultimate invisible object, black holes. By definition, nothing can escape them, not even light. So how in the world are you supposed to study one?
Well, the trick is you don't look for the black hole itself, you look for the mess it's making. All the gas and dust that gets pulled in forms the superheated spinning pancake of matter called an accretion disk. And the friction in this disk heats it up to millions of degrees, causing it to glow incredibly brightly, especially in X-rays. And this is where theory meets observation in just a stunning way. See, the diagram on the left shows what general relativity predicts. Because the disk is spinning so fast, light from the side moving towards us gets its energy boosted, while light from the side moving away gets stretched out. On top of that, the black hole's immense gravity stretches the light even more. All of this combines to smear a sharp peak of light, say from glowing iron atoms, into this very specific lopsided shape. And the graph on the right, that's actual X-ray data. The prediction and the observation, they're a perfect match. As the source material puts it, the unique shape of this light is a direct signature of the warped character of space-time right at the black hole's edge. It means we are literally seeing the effects of extreme gravity written in the language of light. Okay, so we're going from the total chaos at the edge of a black hole to the most orderly objects you can imagine. This final test of general relativity is so precise it actually won a Nobel Prize. And it all comes down to finding a pair of perfect cosmic clocks. So what exactly is a pulsar? Well, it's the super-dense, collapsed core left over after a massive star goes supernova. It's spinning hundreds of times a second, and it sweeps beams of radiation through space. If one of those beams happens to pass by Earth, we see a regular pulse. It's basically a cosmic lighthouse. And when I say regular, I mean unbelievably regular. This number here is the time between pulses for a famous pulsar. We've measured it to 13 decimal places. That makes it a more stable and precise clock than anything we've ever built here on Earth. It's pretty much perfect. A single pulsar is an amazing clock. But back in 1974, astronomers Hulse and Taylor found the absolute holy grail, a pulsar that was orbiting another superdense star. This binary system created the perfect natural laboratory for putting gravity to the test. And this is the Nobel-winning result. See, general relativity predicts that two massive objects orbiting this closely should constantly be churning up space-time, radiating energy away as gravitational waves, actual ripples in the fabric of reality. If the system is losing energy, the two stars have to spiral closer together over time. The solid line on this graph is Einstein's prediction for how fast their orbit should shrink. And the dots? Those are the actual measurements, taken over decades. The match is perfect. This was the first powerful, undeniable evidence that gravitational waves are real. So, after our tour through this cosmic laboratory, what's the final verdict on Einstein's theory of gravity? Well, we've seen three incredible pillars of evidence from all across the cosmos. We saw gravity bending light, creating cosmic mirages that let us weigh the invisible. We saw the warped glow of matter at the very edge of a black hole. And we listened to perfect cosmic clocks as they spiraled closer together, giving us the first smoking gun for gravitational waves. The ultimate takeaway is this: general relativity is not just a theory on a blackboard anymore. It's passed every single test we've thrown at it, from the scale of entire galaxies down to the edge of black holes. It's now a fundamental tool that astronomers use every single day to map out and understand our universe. It just makes you wonder, doesn't it? We've used it to find invisible objects, to peer at black holes, and to hear the faint rumble of space-time itself. What other secrets is the universe hiding, just waiting for us to find them, with gravity as our guide?